Everything you assume about how a guitar works is backwards. An acoustic guitar is built to vibrate. Its whole hollow wooden body is a resonating chamber, designed to shake and breathe and push sound out into the room through that hole in the front. That is the entire point of it. But when Leo Fender built the first mass-produced electric guitar in 1950, he did the exact opposite. He took a solid slab of ash, no sound hole, no hollow chamber, just dense wood. Strum it unplugged, and it is almost silent. Barely a whisper. And that silence is the point. Because the less the body moves, the longer the string keeps ringing, and the cleaner the signal a pickup can pull out of it. The electric guitar is not really an instrument that makes sound. It is a machine that turns a vibrating steel string into electricity. And the engineering hiding underneath those strings is far stranger and far older than almost anyone who plays one realizes. To understand it, you have to start with a piece of physics from 1831. That year, in a laboratory in London, a scientist named Michael Faraday wrapped two coils of wire around opposite sides of an iron ring. When he switched a current on in one coil, a needle on the other side twitched, just for a moment. He had discovered that a changing magnetic field can create electricity in a nearby wire, no battery touching it, no direct connection, just a moving magnetic field, conjuring current out of empty copper. We call it electromagnetic induction, and it is the principle behind electric motors, power plants, and the transformers humming on telephone poles all over the world. It is also the entire secret of the electric guitar. Here is how that 19th century discovery ends up under the strings of a Fender Stratocaster. Sitting beneath the strings is a small bar of magnet wrapped in a coil of incredibly thin copper wire, thousands and thousands of turns of it. That magnet does something clever. It reaches up and magnetizes the steel guitar strings themselves, turning each plain steel string into a tiny temporary magnet hovering right above the coil. Now pluck the string. As it vibrates back and forth over the pickup, it drags its little magnetic field along with it, and a moving magnetic field next to a coil of wire is exactly the situation Faraday found in his lab. The vibrating string induces a tiny electric current in the copper coil, and that current is a perfect electrical copy of the string's motion. Pluck harder. Bigger signal. Play a higher note, faster wiggles in the current. That faint electrical whisper travels down the cable into an amplifier, and only then becomes the sound you actually hear. So the strings are not making the sound. They are generating a code. The amplifier and speaker translate it. But this raises an obvious problem. A vibrating guitar string barely moves. We are talking a fraction of a millimeter of motion. How does a movement that small become a sound loud enough to fill a stadium? This is where the coil earns its keep. A single loop of wire moving through a magnetic field generates an almost laughably small voltage. So, pickup designers do not use one loop. They use somewhere around 5,000 turns of wire so fine it is thinner than a human hair, all stacked together. Each turn adds its own small contribution, and thousands of them in series multiply that tiny signal into something an amplifier can grab onto and blow up enormously. The magnet provides the field. The string provides the motion. And the mountain of copper turns a microscopic flicker into a usable electrical signal. That is the conversion engine. Now back to the strangest part of the whole design. The body. When Leo Fender stripped out the hollow sound box and used a solid plank of wood, he was not just making the guitar easier to build. He was chasing two things at once, and both of them depend on the body staying as still as possible. The first is feedback. A hollow electric guitar, played loud, turns into a problem. Sound waves from the speaker hit the thin wooden top of the guitar. The top vibrates. That vibration shakes the strings. The pickup catches it. The amp makes it louder. And the whole thing spirals into that screaming howl every band has accidentally unleashed at least once. A hollow body is essentially a chamber tuned to feedback. A solid body has no chamber to excite, so it stays controllable even at brutal volumes. That is why you can stand in front of a wall of amplifiers with a solid body guitar and still play a clean note. The second reason is the one that sounds like a contradiction, and it is the heart of this whole video. Sustain is how long a note rings before it dies away. And here is the counterintuitive truth that trips up almost everyone. A guitar string is a closed energy system. When you pluck it, you give it one push of energy, and that is all it gets. From that instant, the energy only drains away. Some of it leaks into the air as faint sound. Some of it is lost to the string flexing against itself. And crucially, some of it bleeds out through the bridge and into the body of the guitar. Every bit of energy that escapes into the body is energy stolen from the string. And a string that has lost its energy stops ringing. So if you want a note to sustain, to hang in the air for a long time, you want a body that refuses to absorb that energy. You want a body that is rigid, dense, and as close to motionless as possible so the energy stays locked in the string, feeding the pickup, instead of dissipating into vibrating wood. A perfectly rigid, perfectly inert body would, in theory, give a string nearly endless sustain. The dead slab is not a compromise. It is the goal. The famous singing sustain of a heavy mahogany Les Paul comes in large part from exactly this. A heavy, stiff body that simply does not give the strings energy anywhere to go. So the acoustic guitar and the electric guitar are solving opposite problems. The acoustic wants to drink in the string's energy and broadcast it to a room. The electric wants to hoard that energy, keep the string ringing, and let a magnet and a coil eavesdrop on it. Same 6 strings, completely inverted engineering. And the man who figured this out commercially could not play a single chord. If this is blowing your mind a little, subscribe. This channel breaks down the hidden engineering inside everyday objects every week. And the guitar is just the beginning. Now let me tell you about the inventors, because the story gets even better. Leo Fender was not a guitarist. He was a radio repairman from Southern California who tinkered with electronics in a small shop. He did not approach the guitar like a musician trying to express himself. He approached it like an engineer staring at a broken product. Musicians wanted something loud, durable, feedback-resistant, easy to repair, and cheap to manufacture. So Fender essentially ignored centuries of luthier tradition and built a solid-body electric guitar in his workshop, with a simple bolt-on neck and a flat slab body that any factory worker could produce consistently. People in the industry thought he had lost his mind. Everyone knew a guitar was supposed to be hollow. He proved them all wrong, and his design template is still the standard 3/4 of a century later. But Fender's early pickups, and Gibson's, all shared the same irritating flaw. They used a single coil of wire. And a single coil is fantastic at its job, which unfortunately includes a job nobody asked for. It acts like an antenna. The electrical wiring in the walls of any room runs on alternating current, cycling 60 times a second in North America. That current throws off a faint electromagnetic field, and so do lights, transformers, and neon signs. A single coil pickup, sitting there as a big sensitive coil of wire, happily picks up all of that interference along with the guitar. The result is a constant, maddening hum underneath everything you play, a low electrical buzz that got worse the louder you turned up. For early electric guitarists, it was just the price of plugging in. Until 1955, when a Gibson engineer named Seth Lover got fed up with it. Lover was not a rock star. He was a quiet electronics man who had tested amplifiers at the Gibson factory as a young man, served in the Navy during the war, and come back to design circuits. He already knew a trick from amplifier design, a way of using 2 coils to cancel out unwanted noise. And he had a hunch the same idea could work inside a guitar pickup. His insight was elegant. If one coil picks up the hum, then a second coil, wound in the opposite direction and with its magnetic polarity flipped, will pick up that same hum as a mirror image. Wire the 2 together, and the hum from one cancels the hum from the other. The interference cancels itself out and vanishes. But the signal from the guitar strings, because of the way the magnets are arranged, does not cancel. It adds together. The noise disappears, and the music gets stronger. He called it the humbucker, because it bucked the hum. Gibson filed the patent in the summer of 1955. Lover thought he had solved a technical annoyance, a noise problem, an engineering footnote. What he had actually done was invent the sound of rock and roll. Because that second coil did something he had not really set out to do. Two coils together produce a fatter, louder, warmer signal than one. Where a single coil is bright, glassy, and thin, the humbucker is thick, dark, and powerful. Push that beefier signal into an overdriven amplifier, and you get the rich, saturated roar that became the voice of hard rock and heavy metal. The crunch of a Les Paul through a cranked amp, the thunder of countless rock records, traces straight back to a Gibson engineer trying to silence a buzz. A noise-canceling fix accidentally became the most worshipped tone in electric guitar history. And that is the recurring theme of this whole machine. The decisions that defined how guitars sound were often solutions to dull, practical engineering problems that turned out to have musical magic hidden inside them. Take the magnets. The early pickups used a material called alnico, an alloy of aluminum, nickel, and cobalt. Engineers picked it for stable, reliable magnetism. But it turns out the specific strength of that magnet shapes the tone. A stronger magnet pulls harder on the strings and brightens the sound. A softer one rounds it off and warms it up. Builders now choose between different grades of alnico, or harder ceramic magnets, the way a chef chooses spices, each one nudging the character of the sound. Even where you place the pickup changes everything, for a reason rooted in basic wave physics. A vibrating string does not move uniformly along its length. Near the bridge, where the string is anchored tight, it barely moves. So a pickup there hears mostly the sharp, bright, treble, heavy edge of the vibration. That is the twang, the bite, the cut. Up near the neck, the string swings in a wide arc, so a pickup there hears a fuller, rounder, bassier tone. That is why nearly every electric guitar has a switch. You are not changing the strings. You are choosing which part of the string's motion the magnet gets to listen to. So when you really look at it, an electric guitar is a stack of clever compromises hiding in plain sight. A body engineered to stay dead so the strings can stay alive. A magnet that turns ordinary steel into a transmitter. A coil of hair, thin copper, performing a trick discovered in a Victorian laboratory. A noise-canceling circuit that became an art form. None of it looks like technology. It looks like a wooden plank with some wire on it. But every curve and material and measurement is doing a job. The next time you hear a guitar scream through a solid body in a stack of amps, remember what is actually happening. A steel string is moving a fraction of a millimeter. A magnetic field is being disturbed. A current is being born in copper. And a 200-year-old discovery about magnets in motion is quietly powering the loudest music ever made. All from an instrument that works best when it barely moves at all.